Hello students. So today we'll discuss the Lagrangian interpolation polynomial. So what is this Lagrangian interpolation polynomial? It is used to derive the shape function. So in the earlier class we have seen what is shape function and even the other method to derive the shape function. So this Lagrangian interpolation polynomial is one more method to derive the shape functions of a given element. Okay. So this method is used to derive the shape function for elements having higher order of nodes. The Lagrangian interpolation polynomial can be given as ni of zeta is equals to pi, j is equals to 0 to n, and j should not be equals to I. I repeat, pi, j should be equals to 0 to nth term, and j should not be equals to I. In general, the expression is given as zeta minus zeta j divided by zeta I minus zeta j. Now what is this I and j? I is the number of nodes that is there in the element. For example, if it has nth node in an element, and the numerator you keep on writing this term up to the nth term. That is zeta minus zeta 1, zeta minus zeta 2, zeta minus zeta 3, that goes on up to the nth term, that is nth node in an element. In the denominator, we have zeta I minus zeta j. Zeta I is the particular node in that nth node. For example, if you have 10 nodes, in that 10 nodes, which node is this? It represents the I. If you're writing for the first node, it is 1. If you're writing for the second node, it is 2. It is like that. Okay. So in the denominator, zeta I minus zeta 1, zeta I minus zeta 2 goes on up to zeta I minus zeta n. So here you can see I have written one more term here, zeta minus zeta I minus 1 and zeta minus zeta I plus 1 divided by zeta I minus zeta I minus 1, because whatever it is there in the numerator, that is j, should be there in the denominator, that is j. So here I have written j as I minus 1 and I plus 1. That is because j should not be equals to I. So since j should not be equals to I, j can be either one term minus I or one term plus I. Understood? That's why this in general I have written like this. So this is general expression, zeta minus zeta I minus 1 divided by zeta I minus zeta I minus 1, zeta minus zeta I plus 1. It cannot be equals to j cannot be equals to I. So zeta minus zeta I plus 1 divided by zeta I minus zeta I plus 1. So this is a general expression. You might have to remember this general expression. In the next line, what we have is where I is equals to 1, 2, 3 up to n, that is till the nth node how many nodes we have, that one, and n is equals to number of nodes in an element. Okay. Next Lagrangian polynomial is Lagrangian polynomial given by equation 1. This is the equation 1, is an alternative method to find the shape function of a given element in local or global coordinates. So I've said you this is one more method to derive the shape function in the local or the global coordinate. So the one more method we have already discussed in the class. Okay. So now we will look on to the okay. So now we look on to an derivation. So first, Lagrangian interpolation polynomial, Lagrangian interpolation function for linear element. So first we'll derive the shape function for a linear element. The shape function for two-noded bar element. So in the exam, if he has asked you to write the shape function for a linear element, then you have to consider it as a two-noded bar element. Is that fine? So two-noded bar element, we have an element here and it has two nodes. This is node number 1 and this is node number 2. So this will be zeta 1 and this will be zeta 2. Okay, and it is in the local coordinate. So it is it is in the local coordinate or in the natural coordinate system. So in the natural coordinate system, what we write it as in the form of zeta and neta. So since it is an 1D element, we have only zeta axis here. Is that fine? So now consider two-noded bar element as shown in figure. So this is a two-noded bar element as shown in the figure. The natural coordinates of nodes 1 and 2, the natural coordinates of nodes 1 and 2 are -1 and +1. So you have to remember this, or you have to know this. So already we have explained in the class that, see, in the natural coordinate system, the coordinates always varies from -1 to +1. The coordinates always varies from -1 to +1, and in between it will be 0. Zeta is equals to 0. We are not representing that here because it has only two nodes, 1 and 2. So this middle node we don't have here. Is that fine? So the natural coordinates of nodes 1 and 2 are -1 and +1. Also, consider the natural coordinates at the center of the element as 0. That's what I said. At the center of the element, we have to consider it as 0, and the zeta values always varies from -1 to +1 in the natural coordinate system. Okay. So now, using the Lagrangian interpolation polynomial. So using Lagrangian polynomial, we have the formula ni of zeta. Ni of zeta is equals to pi, j is equals to 0 to n, j should not be equals to I, zeta minus zeta j divided by zeta I minus zeta j. So you have to write this general expression before deriving it. So now let us put the terms in this general expression. Now for the given element, so this is a given element. For the given element, how many nodes we have? We have 2 nodes. So n will be equals to 2. That is up to the nth node. We have only 2 nodes. So n will be equals to 2. So now consider node 1. So this is not element, this is node. Consider node 1. So considering node 1, I is equals to 1. So when you are writing for the first node, I will be equals to 1. Similarly, when you are writing for the second node, I will be equals to 2. Is that fine? So now in this formula, you got to know the value of I. And the value of j is the number of nodes in it. Okay, is the number of nodes in it. So now just substitute the values. So for the first node, I is equals to 1. So ni of zeta is nothing but n1, because I is equals to 1. n1 is equals to zeta minus, what is j? J is the number of nodes. We have 2 nodes here, so we have to write for 1 and we have to write for 2. What if we write for 1? For example, if we write zeta minus zeta 1 divided by zeta 1 minus zeta 1, then I'll have j will be equals to I. Okay, so this first term I'm skipping here. Understood? So that's why I'm moving on to the second term. So in the second term, what I have is zeta minus zeta 2. J is 2. Zeta minus zeta 2 divided by zeta 1, because I is 1. Zeta 1 minus zeta 2. Is this clear? Is this clear? See, or in simple you can understand that when you are writing for I is equals to 1, in the numerator don't write the first term, that is zeta minus zeta 1. Understood? Only the second term exists in the numerator. Similarly in the denominator. In the denominator zeta 1, you have I is equals to 1. I is equals to 1. So you will have zeta 1. And whatever you have in the numerator, that will be in the denominator, because zeta j and zeta j. Zeta j and zeta j. Is this clear? Yeah. Okay. So now just substitute the values of zeta 1 and zeta 2 in the equation. So n1 is equals to zeta minus zeta 2. What is zeta 2? Zeta 2 is plus 1 and zeta 1 is minus 1. So substitute these values here. You will have n1 is equals to zeta minus 1 divided by zeta 1 is minus 1 and zeta 2 is plus 1. So zeta 1 minus zeta 2. So minus 1 minus 1. Simplify this, you will have 1 minus zeta divided by 2. In the denominator, you will have minus 2, negative goes to the numerator. So you just change the terms 1 minus zeta. So n1 is equals to 1 minus zeta. Is this clear? Similarly, n2. So similarly, n2. So consider node 2. Consider node 2. So here for the node 2, I is equals to 2. So I is equals to 2. So n2 is equals to zeta minus zeta 1 divided by zeta 2 minus zeta 1. Zeta 2 minus zeta 1. We will not have the second term because in the second term it will be zeta minus zeta 2 divided by zeta 2 minus zeta 2. So this zeta 2 and in the zeta 2 both will be same, that is j will be equals to I. So as per our general expression, j should not be equals to I. That's why you cannot write that term. So substituting the values here, n2 is equals to zeta plus 1 because zeta 1 is minus 1, so minus into minus becomes plus, divided by zeta 2 is plus 1 and zeta 1 is minus 1, that becomes plus 1 here. So n2 becomes zeta plus 1 by 2 or 1 plus zeta by 2, anything is fine. So you got the two shape functions n1 and n2. So these two nodes will have two shape functions. Then you have to write the variation of shape function. This is the variation of the shape function. So for n1, the variation of the shape function, just write the element 1 and 2. And according to the property of the shape function, we have seen that when you are writing for n1, when you are writing for n1, this is for n2 or node 2. So when you are writing for node 1, the shape function is maximum at that particular node and it is 0 at other nodes. Okay, so you have to remember this. You know that according to the properties of the shape function, when you are writing for the node 1, the shape function is maximum at that particular node and it is 0 at the other nodes. So when you are writing for node 1, just write maximum at that particular node and drop down to 0 at the second node. So this is n1 is equals to 1, that is n1 is equals to 1 minus zeta by 2. So here n1 is equals to 1 and n2 is equals to 0. Similarly, when you are writing for node 2, the shape function is maximum at node 2 and it is 0 at node 1. So at node 2 it is 1 and at the other nodes it is 0. So n2 is equals to 1 plus zeta by 2 or zeta plus 1 divided by 2.